Mass is an intrinsic property of an object. Mass is an intrinsic property of an object. Basically, any solid object is made up of atoms, and every atom has an inherent amount of mass based on the number of protons and neutrons and electrons. If you add up the total number of atoms in an object, you can find the total mass of the object, and that's something that is going to be constant as long as the object is constant. Any two objects that have mass are going to have a long-range attractive force between them. This force is the force of gravity. If we consider two objects like we have here with mass m1 and m2 that are separated by a distance r, then the magnitude of the gravitational force between them is this equation here. You'll want to write this down. This is a capital G times m1 times m2, the masses, divided by r squared, where r is the distance between the two. In this case, G is equal to 6.67 times 10 to the negative 11, and G is the universal gravitational constant. This equation here is called Newton's law of universal gravitation. It's something that he developed alongside his laws. Notice that capital G here, the universal gravitational constant, is very small. 10 to the negative 11 is a very small amount, and so usually you need very large objects like a moon or a planet to have enough mass so that when you multiply that mass by a small number, you get a noticeable amount of force. Also notice that this isn't the force of one object on the other, but really the forces of each object on the other. These two forces are an action-reaction pair, and so they are equal in magnitude and opposite in direction per Newton's third law. If we consider the special case of a sphere with spherically symmetric mass distribution, so basically we have a sphere here, and the mass is distributed symmetrically. Spherically symmetric means that you could have a radial dependence, you could have different mass densities at different depths, but if you look at the sphere from any direction, it should look symmetric to any other direction. That's what we mean here by spherically symmetric. And so if we have a distribution like this, and we want to find the gravitational attraction of any object anywhere outside of that mass distribution, what we can do is replace this sphere by a particle of equal mass that should exist at the sphere's center. Basically, that is the sphere's center of mass, which we'll see a lot more coming up. And what we can do is replace our sphere with a particle. Right here in the middle, there's the same amount of mass, but all that mass is all in one spot. That's what a center of mass is. And we can find a same force of attraction on some other object that is outside the object. If you wanted to find the gravitational force inside the distribution, then the calculation's a little bit more difficult. But outside the distribution, it doesn't matter if you have the spherically symmetric distribution or just a point particle. So this is obviously a simpler model. That is how we will simplify problems like this. If we talk about a person who's on the Earth, when we talk about the gravitational attraction of a person, usually we talk about their weight. By their weight, we mean it's the force of gravity acting on them on a planet's surface. If we wanted to find a person's weight here, which is their gravitational attraction to the Earth, what we would do is use the same model that we just discussed. We would have replaced the Earth with a particle at the center of the Earth with the same mass as the mass of the Earth. Our person here is still on the surface of the Earth, and so they are 1 Earth radius away from the mass of the Earth, which is now a particle at the center of the Earth. And so the Newton's law of gravity, of universal gravitation, tells us that their force of gravity acting on them should be the universal gravitational constant times the mass of one object, which is the Earth, times the mass of the other object, which is the person, times the distance between the two. I should say the distance between their centers. Here we have the center of the Earth. And then here, our person is so small relative to the Earth that we're not really worried about the person's center of mass, which would be in their, in their torso region. So we can find this value here. This is going to be the weight of the person. But what we can say is, okay, here we have the weight of a single person. But what if we want to find the weight of something else? What if we had a dinosaur and we wanted to find the weight of the dinosaur? Well, the dinosaur is also on Earth. It's also an Earth radius away, so these parts of the equation are still the same. The only difference here is that this would be the weight of the dinosaur there. Now, what if we wanted to find the weight of a moai from the Isla de la Pascua? In that case, exact same idea. It's still attracted to Earth. It's still an Earth radius away. And so the only difference is going to be in this term. So what we're noticing here is that this term changes. The mass of the object on the Earth's surface changes depending on which object we're looking at. But this part here is always going to be the same. This is a constant, and these are parameters that are due to the Earth that are going to be the same for any object or any person on the Earth's surface. So we can generalize our equation for the weight of an object, but having identified this term here, that is our acceleration due to gravity. That is the value of g that we have. And if you plug in numbers here for the value of g I gave earlier and the mass and radius of the Earth, you'll find that it's very, very close to the value that we know of for g. We'll see that this is most of the way correct. This is 99% of the way correct, and that we'll see some corrective terms show up later that change this number to the 9.81 that we're used to seeing. But the important part is that the value for g for a planet or any other celestial body, like a moon, like a dwarf planet, that sort of thing, depends on the total mass of that planet, or that object, and also its size or its density, which relate to its radius and how that mass is distributed in the planet. We said that gravity is a force that pulls two objects together. If we have some object that is circling a planet, we can think of all of the mass of that planet as being centered as a particle at the center. And there's a force between the two centers of the object. This is called a central force because this force passes through their centers. The Earth pulls objects towards the center of the Earth in all directions. That's why people in Australia don't fall off the bottom. They're pulled upwards towards the center of the Earth, just like folks in the northern hemisphere are pulled downwards towards the center of the Earth. We're all being pulled towards the center of the Earth. But for most human scale situations, we're not really seeing the curvature of the Earth, right? As we travel around, the direction of our weight or our force of gravity would change direction slightly, but we're used to seeing such a small zoomed in value, part of the Earth's surface, that we can say that the weight is essentially straight down if we're using a flat Earth approximation, which we can do again as long as we're staying within a few kilometers, a few miles of where we are, relatively close to the Earth's surface. So in this case, the weight is always acting straight down. We have a magnitude for the weight here. The vector for the weight is in the negative j hat direction because it's always straight down. If we are talking about moving not in a small area but around the whole Earth, we'll have to take into account this circular aspect, which we'll see later in the class. And finally, a quick example here. We have a rock that has dropped off a third floor balcony, and we want to find its acceleration as it falls. So the first thing we'll do is draw a picture. Here's our rock, and it's falling downward. If we want to find its acceleration, we find acceleration by looking at Newton's laws, looking at what forces are acting on the object and what its acceleration will be as a response to those forces. So we will follow those steps. We'll start by drawing a circle around the object, finding points of contact. There are none, so the only force that we have here is the weight. Since we're falling off a third-story balcony, we're not really going that far or that fast, so we can just ignore drag in this case. The rock is pretty heavy and compact, so the only force that we have here is the weight. The next thing that we'll do is draw a free body diagram. Here's our rock depicted as a particle. We know that that rock is moving downwards and accelerating downwards as it falls. We know that the only force acting on it is the weight. And so we can come up with the equation here that the sum of the forces in the y direction is mass times the acceleration in the y direction. The forces in the y direction are the weight, which is downwards, and that's mass times the acceleration in the y direction. We have an equation for weight. It's mg. And we said that our gravitational mass and our inertial mass are the same thing. Those cancel. And what we find here is that the acceleration of our rock is negative g, which means that the rock is in free fall. So that's what we expect. And basically what we're seeing here is that wherever we could use G for the free fall acceleration, when we are not moving very fast, we're not moving very far close to the Earth's surface, that same free fall model also means that we can use weight is mg. Or I should say the magnitude of the weight is mg, that the weight should be mg downwards. If we're in a situation where we can't use the free fall model, we also can't use this value of g. If we can't use free fall, we would have to use the other value of the gravitational force. That's how I distinguish weight versus gravitational force. Weight is kind of the special case here. Gravitational force is more general.